day. Welcome to another Fluid Mechanics 101 presentation. My name is Tueshes Banda. Pumps are installed on water pipelines to provide the necessary pressure at the beginning of the pipeline to compensate for pipe friction in any elevation head and provide the necessary delivery pressure at the pipeline terminus. If you remember, we said whatever the pressure the pump provides is for it provides the pressure to overcome the frictional loss along the line, also to overcome the elevation differences and to provide the necessary pressure which is required at the end of the pipeline. Pump used on water pipelines are either positive displacement PD type or centrifugal pumps. In the industry, most we use centrifugal pumps, and here and there, especially for dosing, that's where we use the PD pumps. PD pumps generally have higher efficiency, but they have higher maintenance cost and a fixed volume flow rate at any pressure within allowed limits. That's why I'm saying we use PD pumps for dosing, because doses a certain amount of volume, so we have control over, let's say, what dose or 1 liter per hour, 2 liter per hour, you can set it. Centrifugal pumps, on the other hand, are more flexible in terms of flow rates, but have lower efficiency and lower operating and maintenance cost. That's why mainly we use 80% of the time we use centrifugal pumps. The majority of liquid pipelines today are driven by centrifugal pumps, as I mentioned. Since pumps are designed to produce pressure at a given flow rate, so they're designed, pumps are usually designed to give a flow rate and provide a certain pressure at that flow rate. An important characteristic of a pump is its performance curve. The performance curve is a graphic representation of how the pressure generated by a pump varies with its flow rate. So a centrifugal pump doesn't have one operating point. It has numerous operating points, but usually operated at its best efficiency point. Other parameters such as efficiency and horsepower are also considered as part of the pump performance curve. Positive displacement pumps. Positive displacement pumps include piston pumps, gear pumps, and screw pumps. These are used generally in applications where a constant volume of liquid must be pumped against a fixed or variable pressure. PD pumps can effectively generate any amount of pressure at the fixed flow rate, which depends on its geometry, which means your pipe size, as long as equipment pressure limits are not exceeded. Otherwise, your pipeline will burst. Since a PD pump can generate any pressure required, we must ensure that proper pressure control devices are installed to prevent rupture of the piping on the discharge side of the PD pump. As indicated earlier, PD pumps have less flexibility with flow rates and higher maintenance cost. Hence, they are not mainly used unless where necessary. Because of these reasons, PD pumps are not popular in long distance and distribution water pipelines. Centrifugal pumps are preferred due to their flexibility and low operating cost. Centrifugal pumps. Centrifugal pumps consist of one or more rotating impellers contained in a casing or pump cover. The centrifugal force of rotation generates the pressure in the liquid as it goes from the suction side to the discharge side of the pump. Centrifugal pumps have a wide range of operating flow rates with fairly good efficiency. The operating and maintenance cost of a centrifugal pump is lower than that of a PD pump. Hence, it's mainly used in industry. The performance curve of a centrifugal pump consists of head versus capacity, efficiency versus capacity, BHP versus capacity. So, which means these are your head, your capacity, your efficiency. Your head, your efficiency, and brake horsepower. they are plotted against that of capacity. The term capacity is used synonymously with flow rate in connection with the centrifugal pumps. Also, the term head is used in preference to pressure when dealing with centrifugal pumps. It's because if I tell you that this pump can provide so much head, it means regardless of the liquid, it will give you that much head, but pressure will be different. So that's why we specify head instead of your pressure. Figure below shows a typical performance curve for a centrifugal pump. As I mentioned earlier, you see your head is plotted against your flow rate. Also, your efficiency here against your flow rate, same as your BHP against flow rate. So this is at 100%. It cannot operate at 100%. So the best efficient point will occur at 90%, which is here. All right. Which is this is the efficiency curve. We come down to the head versus capacity, which means a BEP will have so much head, so much flow rate. And also you can rate your horsepower over the side. So this is a fundamental curve which every engineer should know, regardless of which type of engineer you are. Generally, the head capacity curve of a centrifugal pump is a dropping curve. You see, it's a dropping curve, which means it's going down as your flow rate, or the head decreases as your flow rate increases. The highest head is generated at zero flow rate, which we call it shut-off head, and the head decreases with an increase in the flow rate as shown in figure above. So when your flow rate is zero, you have your maximum head, we call it shut-off head. The efficiency increases flow rate up to the best efficient point, BEP, after which the efficient drops. So efficient will increase, you see BEP here, then it starts to drop. The BHP also generally increases the flow rate, but may taper off or start decreasing at some point depending on the head capacity curve. Affinity loss. The head generated by a centrifugal pump depends on the diameter of the pump impeller and the speed at which the impeller runs. So the head generated by a centrifugal pump, it depends mainly on your impeller size and also the speed of rotation of your motor. The affinity laws of centrifugal pumps may be used to determine pump performance at different impeller diameters and pump speeds. These laws can be mathematically stated as follows for impeller diameter change flow rate, which is Q1 flow rate at 1 over Q2 is equal to D1 over D2, ratio of flow rates over ratio of diameters. As for head, it's ratio of heads times ratio of diameters squared. For brake horsepower, so it's a ratio of brake horsepower from 0.1 relative to 0.2, and ratio of diameters to the power of 3. For impeller speed change, ratio of flow rates, the same as ratio of your motor speed. Heads, ratio of heads is the same as of ratio of motor speed squared. Brake horsepower is the same as ratio of brake horsepower to that of pump speed, motor speed to the power of 3. Where subscript 1 refers to initial conditions and subscript 2 to final conditions. It must be noted that the affinity laws for impeller diameter change are accurate only for small changes in diameter. So your changes of diameter should be too much, or at least a 10% change is reasonable, but you can't take a 20% impeller size, reduce it to 10, which is 50% reduction. The affinity laws won't give you accurate results. However, the affinity laws for impeller speed change are accurate for a wide range of impeller speeds. So it's, for impeller speeds, it's better. You can have humongous changes. Using the affinity laws, if the performance of a pump is known at a particular diameter, the corresponding performance at a slightly smaller diameter or slightly larger diameter can be calculated very easily. Similarly, if the pump performance for a 10-inch impeller at 3,500 revolutions per minute impeller speed is known, we can easily calculate the performance of the same pump, 4,000 revolutions per minute. Example, on the performance of a centrifugal pump with 10-inch impeller is shown in the following table. So we have these points and their corresponding efficiencies. Determine the revised pump performance with reduced impeller size of 9-inch. What will be your capacity? What will be your head? Efficiency will not change because we are taking these points on the ISO efficiency graph, which means the efficiency is constant. If the given performance is based on impeller speed of 3,560 revolutions per minute, calculate the revised performance at an impeller speed of 3,000 revolutions per minute. So if you remember the ratio of impeller diameters, because we want to corresponding Q, so it's D2 over D1. D2 will give you that is 9 inches, D1 was 10, so it's 0.9. Therefore, the Q values will be multiplied by 0.9. So you multiply all these Q values by 0.9. You get this. And the head values will be multiplied by, remember it's square, so it's 0.9 by 0.9 by 0.1. Then we get this. Remember, ISO efficiency. So revised performance data are given in the following table. When speed is changed from 3,560 to 3,000 revolutions per minute, the speed ratio is also speed 2 over speed 2, N2 over N1. The ratio is this. Therefore, Q values will be multiplied by 0.842. The H values will be multiplied by, remember, is that squared. So squared. Then your efficiencies, they do not change. Therefore, the reverse pump performance is shown be low for change of speed. Example 2. For the same pump performance described in previous example, calculate the impeller trim necessary to produce a head of 2,000 feet at a flow rate of 3,200 gal per minute. If this pump had a variable speed drive and the given performance was based on impeller speed of 3,160, what speed would be required to achieve the same design point of 2,000 feet and a flow rate of 3,200, which means our point 2, this is our H2, this is our Q2. So we need to find out what's our Q1, Q2. So remember the 2,000, it's our H2. So what H1, you go to the example there. H1, we used 79 because this is the highest point. So we took the 79% as the BEP or best efficiency point, right? So which means this pump was operating at its BEP is this one, 2115, and also it's 3,200. It's a flow rate, right? Then 2115 there, and our Q is 3,200. So which means our ratio is 2,000 over 2115. Then we get our D is equals to 10, right, times 0.9705, which is equal to 9.72, right, which means this over this, then to the power of 5 to remove that, then multiply by 10, you get that. Then the speed ratio can be calculated from, remember it's N2 over N1, N1 3560, right? N2, that's what we are looking. also h1 over h2, sorry, h2 over h1, right? Solving for speed, we get that, which is 3,562 revolutions per minute. Strictly speaking, this approach is only approximate since the affinity laws have been applied along iso efficiency curves, which means we are assuming our efficiencies do not change, they remain the same. We must create a new HQ curves at the reduced impeller diameter or speed to ensure that at 3,200 thou per minute, the head generated is 2,000 feet. If not, adjustment must be made to the impeller diameter or speed. Thank you for watching. And if you have any queries, additions, or subtractions, do not hesitate to contact me on my email address, which is tubasfund@gmail.com. Please like, subscribe, and comment to my YouTube channel to learn more data engineering stuff. I'm out. Thank you.